So we've got this rotor plate here. This thing weighs almost 2 kilograms and it rests on these 3 tilting pads. They can tilt on these ball bearings here. I'm going to go off on a quick tangent. Look what happens when I lift the rotor off those pads. The pads stick to the rotor and they eventually fall off. That's because they're ringing together. These surfaces are incredibly flat to a tolerance of around 100 nanometers. And you could do something similar with gauge blocks. I've got a couple of gauge blocks here. They're precision width blocks of metal, and so the end faces are incredibly flat. When you press them together, well, they stick. That's called gauge block ringing, and we can see something similar here. If I try and turn the rotor, there's a decent amount of resistance because it's nearly 2 kilograms. But watch what happens when I give it a proper spin. Isn't that amazing? This thing will spin for over a minute because it's floating on a cushion of air that's about 3 or 4 microns thick, according to Tom's calculations. We can actually prove the thing is floating using this device here. This is what Tom calls his octo continuity checker, and it's just a little LED light. There's a battery inside, and some cables have been drawn out so that you can complete the circuit from the outside. Look, there we go. The light turns on when we complete the circuit. So we can feed this through the bearing to see if the circuit breaks when we spin it. This is an insulating rod, so if we connect the LED to the top and the bottom and the LED turns on, we know that's because the circuit is being completed through the bearing. In other words, the rotor is touching the pads when it's at rest. So let's spin up the rotor and see what happens. There you go, the LED turns off. As the rotor slows down, you start to see flashes of the LED as the rotor occasionally touches the pads. And those flashes increase as the rotor slows down until eventually you get a solid light and the rotor stops. Handheld bearings like this were built as a marketing tool so that salespeople could sell much larger versions for use in industry, like to support a turbine in a hydroelectric plant that might weigh hundreds of tons. Because the pads are able to tilt, they form a wedge-shaped cavity, which I've shown in an exaggerated form here, and it means that the air that is pulled through is forced into an increasingly narrow space. Hydroplaning or aquaplaning works by a similar principle. So does ice skating. When an ice skate runs over the ice, it melts the ice, so you have a layer of water between the skate and the ice. It's also the working principle of this playing card that I've slightly turned the end up of. The original Hyperloop concept was based on this idea as well, though it isn't anymore. So there you go, the hydrodynamic bearing crops up in all sorts of strange places.